Hey students, I've had a couple questions here about really how to follow up on that static equilibrium lab. So I thought I would take one of the data sheets that I sent you. This is the three forces, and it didn't print very dark, but I hope you're seeing kind of the grid lines. And so I sent this to you as well as another one that was in balance that had four forces. But I think if I talk about this one with three, you'll be able to do the four. In fact, it might look better on camera if I turn it this way, although the camera's not wide enough to pick up everything. But the steps you have to do with forces and torque. And the first one I didn't get any questions on. So I think you guys understood that if you add up all the forces in the x direction and add up all the forces in the y direction, you'll get a small number. So on that one, for example, force number 1, you would have a positive x and a positive y. For force number 2, you would have a big negative x and a positive y. And for force number 3 over here, you would have a negative y and a positive x. So you find each of those components, of course, by getting a protractor and measuring some angle. Like for force number 1, maybe I'd put it here on my grid and then get this angle. So I'm gonna trust that you are doing the forces right, because like I said, nobody asked about that. But some people were wondering how to do the torques, and that makes sense because that's the new stuff and the hard stuff. So I would suggest that you start off by picking the middle here, and you're asked to calculate the torque as measured from the middle point. Maybe I'll write this as the torque from this force here, which would be number 2, so torque number 2. And then maybe I do a torque from number 1. So this is torque from number 1. And then this over here is torque from number 3. Okay. And you calculate torques by measuring their perpendicular distance and then how much force you have. So this must be force number 2 and the perpendicular distance to number 2. And let me kind of show you what that would look like. Now, force number 2 is pretty easy. It's just the number, I measured and gave to you would be this 2.45. But the perpendicular distance is what you've got to use the graph paper for. And so you want to measure the distance from this pivot point to the line of action. And so it would look something like this. And maybe to help you make sure you're perpendicular, you can lay out the protractor. And get a perpendicular distance. And it looked like that was about 2.2 centimeters. So I'll write it as 0.022 meters. So the torque from number 2 then would be 0.022 meters times the force, 2.45 newtons. And then let's not forget the sign for a moment. That might be kind of the hardest thing. So imagine putting your finger on it and then grabbing the paper and pull it in the direction of force number 2. And I hope you see it would spin my paper in a counterclockwise direction, which we usually label counterclockwise as a plus. So I would say the first torque is whatever this multiplies out to be, and a positive torque. Now, for number 1, And I'll need to do maybe something like this. Here's the line of action. Let's see if I can mark the perpendicular distance careful enough. And so I'll call that perpendicular distance number 1. And that's looking like what? About 7.5 centimeters. So it goes 0.075 meters. The amount of force is 2.45 newtons. And the direction, and I want to emphasize, the direction has to do with how it rotates it, not which way it's pointing. So like back here on number 2, notice the force was kind of in a negative x direction and a little positive y. But I gave it a positive torque because of the direction it rotates. And same thing here. If you imagine putting your finger on this and then pulling it, this is going to make the paper rotate in a clockwise direction. So that would be a negative torque. Okay, so the third torque would again be the perpendicular distance to this line of action. So maybe we're looking at something like this. And so this would be our perpendicular number 3. And the distance would be, looks like 11.0 centimeters. So 0.110 meters. And the amount of force is 0.98 newtons. Now again, whether it's positive or negative has nothing to do with what direction of the force is, which kind of is down, negative. It has to do with how it would rotate it. So if I put my finger at the pivot point and my other hand pull the force, it would rotate the paper in a counterclockwise direction. And that's the positive. So then I would add these 3 together. And so it would look something like this. 0.022 times 2.45 minus 0.075 times 2.45 plus 0.11 times 0.98. And so I get something that's kind of close to 0. I mean, in terms of decimal, it's 0.022. And if you were to look at maybe if all of them were added together, you would be, you know, way up here in this decimal place. So I'm over 10 times smaller than it. Maybe even quite a bit more than if they were just kind of added straight up. So I'd say this number is small compared to what it could have been. And so it worked. The sum of the torques is 0, or at least in my measurement is close to 0. Okay. And then you're asked to do this same logic with some other axis. Pick any one you want. I think the first one's just kind of natural to pick the center, because this was kind of the gist of what I was saying in the lab, is that you might pick a point here and thinking the torque has to be 0 around some magical point like the center. But see, since it doesn't rotate around any point, the reality is the torque would be 0 around every point. So pick any random point. I know that in the video of the lab I was preparing, I picked way down here in this corner. Now, I'm not so sure that was good advice, because then you might end up drawing things that are off the paper. For example, if I did pick down here, the line of action of number 1 here would come across, and the perpendicular distance would be something like over here somewhere. And it's off my paper. I can put another piece of paper under there to deal with that. So if you want to do down here, like I said, fine. But maybe I should just say something like, pick another point. Have fun with it. Pick any point. But not necessarily the edge of the paper, because there's a good chance it would go off. So let's pick this. And so I won't take the time to accurately draw or measure these, but you can kind of see from this pivot and perpendicular to this line of action would probably be something like this. So this would become our perpendicular number 3. And so I would have a different value here. I still would have the same amount of force. And I might even have changed the plus or minus depending on where I pick this point. So let's see. If I put my finger on it and pull it here, looks like it still spins it in a counterclockwise direction. So it turns out that one's still positive. But don't be surprised if that changes depending on where you put this point. But what hopefully doesn't change is that if you do all 3 of them as measured from this point, you'll get something close to 0. So torque number 1, you might have to kind of extend this line of action out here so that you can draw something that kind of looks perpendicular. And don't just eyeball it. Do a little better, okay, like I did with the red one. But this now would be our perpendicular number 1. And again, definitely this R has changed. The force remains the same. The sign may have changed, but it didn't. It looks like it's still, when I pull on it, it goes clockwise, which is negative. And then torque number 1, yeah, still negative. Okay, I was like, wait a minute. Okay, I just got those in wrong order. Okay, yeah, so torque number 1 is still negative. And torque number 2, I guess, would perpendicular distance might look something like, well, can eyeball it, something pretty good, maybe something like that. So again, this would be R2 perpendicular. And again, this number will now have changed. This would still be the same. And the sign could change, but it doesn't look like that did either. So that's a positive still. Okay. So without me measuring those, you should have torque number 1 in green, torque number 2 in green, and torque number 3 in green, and add them up and get something small. Saying that in a perfect world, it would have come out to be 0. And so 2 torque calculations, and then I'll say 2 force, but it's really 1 force in the X and 1 force in the Y. And then do the same thing for the other balancing sheet I gave you, but this time you're going to have 4 forces. So you'll have 4 torques here and 4 torques here, and you'll have 4 terms for the X and 4 terms for the Y. But again, should come out to be 0 for all those cases. Okay, so hope that helps with any clarification on what to do on this static equilibrium lab, and helps you see torques, because this is chapter 9. This is one of the challenging things with the torque.